Hello, everybody. This is Paul again, and welcome back to another fast tutorial. So today we're going to be talking about propulsion architecture matrices. And so in the previous videos, we introduced fast how you can create an aircraft specification file and how you can prescribe a mission profile. One of the things that we haven't touched on yet is how do you prescribe a propulsion architecture that is not shipped with FAST. So FAST provides 6 different propulsion architectures: a conventional, electric, fully turboelectric, partially turboelectric, series hybrid, and parallel hybrid. But what if you want to make a propulsion architecture on your own? So the answer is you have to use these propulsion architecture matrices that I'm going to show you. So this tutorial is going to be broken up into 2 parts. This part is going to focus on learning about the propulsion architecture matrices and what each one is for. And then in the next video or tutorial, what we'll do is make a new propulsion architecture using the knowledge we learned from this tutorial. All right, so without any further ado, let's get started. And before I go into any detail about the propulsion architecture matrices, I do want to refer everyone to a paper to read more details about this. The citation will be on the next slide, but I do just want to show you the PDF of it. It is entitled "A Framework for Electrified Propulsion Architecture and Operation Analysis," and the citation will be on the next slide I go to. But this paper contains all of the detailed information about the propulsion architecture matrices I am going to show you. And the key with the work in this paper is that every propulsion architecture can be represented as a set of matrices, which comes from a graph theory inspired approach. So without any further, let's look at a propulsion architecture. And in this example, we see that we have a battery and fuel, an electric motor and turboshaft engine, and a propeller or a fan. And the first thing is that we need to group these components based on what they do. So the battery and fuel are energy sources because they are providing energy to the system. So the battery and fuel are providing energy to ultimately turn the propeller or fan. Now, the power sources, such as the electric motor and turboshaft, are converting that chemical energy into mechanical energy. Okay? So the power sources are converting chemical to mechanical, and it's the connection from the power sources to the thrust sources that actually spin the propeller and fan. The thrust sources, i.e. the propeller or fan, are what actually generate thrust on the aircraft. So the key components that we want to look at in any propulsion architecture are the energy sources, the power sources, and the thrust sources. So let's look at a few more propulsion architectures now. You'll notice that all of these can be grouped, or all of the components can be grouped into energy sources, power sources, and thrust sources. So in the parallel hybrid example here, we have the battery connecting to an electric motor. So we're converting chemical to mechanical. And then the electric motor connects to a gearbox, which spins the propeller or fan. Similar thing with the fuel. They're both, the fuel is turning the turboshaft, which then plugs into the gearbox as well to spin the fan. And that's why we call this a parallel hybrid, because there's 2 power sources working in parallel, and they're connected by the gearbox. For the turboelectric configuration, we only have one energy source, and that's fuel, which spins the turboshaft. So we're converting chemical to mechanical. And then what happens is we have an electric generator, which converts the mechanical energy to electrical energy, which then connects to an electric motor, converting that electrical energy back into mechanical energy to spin the propeller or fan. Similarly, we can have a series hybrid configuration. So instead of putting the electric motor in parallel to the turboshaft engine, I can take the series wiring like I did from the turboelectric configuration, but also supplement the electric motor power with a battery. So as you can see, each of these electrified propulsion architectures has a different set of connections, and we need a general way to represent these. And that's where these matrices inspired from graph theory come into play. So there's going to be four different matrices to show the power flow. And when we think about the power flow, we want to think of it going downstream from the thrust sources to the energy sources. So you can imagine that we're flying along and we have some power required that we need to achieve to fly. The thrust source has to generate that power in order to propel the aircraft forward, and the downstream components, the power sources and energy sources, must provide that power. So for a little bit of terminology from the paper that I showed earlier, the matrices with A are called property matrices, and these describe a physical quantity that is calculated from some sort of physics-based model. So in this case, a matrix would represent the power required to be produced by each component. Then there's also interdependency matrices, which are represented by B. And these show the connections to create the flow paths that we were talking about. So what we can do is use the property matrices, these A's, along with the interdependency matrices, the B's, which show the flow, to propagate energy from the thrust sources all the way back to the energy sources. And the really nice thing about these matrices is that it can be used to express, create, and operate any propulsion architecture you want. So before we go on to look at some examples, there's one more thing I would like to clarify. The energy sources and thrust sources are pretty self-explanatory, but you'll notice here that we have two matrices for power sources. We have a driving power source and a driven power source. Now you may be asking, well, what's the difference between those? A driving power source could be supplementing power to another power source. So in the turboelectric example we have here, the turboshaft engine is actually driving the generator, and then the generator is driving the electric motor. So the turboshaft is a driving power source. The generator is driven by the turboshaft, but it's also a driving source because it drives the electric motor. And then the electric motor is a driven power source because it is being driven by the generator. In the case of the parallel hybrid configuration, we don't have any power sources wired in series. So each of the power sources are just driving. They are driving themselves. In the series hybrid case, we have a similar setup to the turboelectric. So the turboshaft drives the generator and the generator drives the electric motor. So now that we've gone through what the architecture matrices describe, we now are going to try to create them. So the A matrices, the property matrices, will come from your physics-based model. Those are going to be properties that fast computes in the mission analysis. However, you need to describe the B matrices ahead of time. And the B matrices, remember, are those interdependency matrices. So we're going to take a look at the next slide and figure out how to assemble those matrices. So these matrices, again, define the architecture by establishing these physical connections between sources. So any entry in the matrix with a 1 indicates a connection between two components. Then any value or entry with a 0 indicates that there is not a connection. So let's start off by looking at the parallel hybrid case here. If we go back to the previous slide for just 1 second, we'll see that there are 3 B matrices we have to create. The first one represents the connections between the thrust sources, TS, and the driven power sources, PS. The next matrix shows the connections between the driving power sources and the driven power sources. And then the last matrix shows the connections between the power sources and the energy sources. So let's first look at the connections between the thrust sources and the power sources. In the parallel hybrid configuration, the propeller is connected to both the electric motor and the turboshaft engine, which is why we have a 1 in both entries. You'll also note that the TS-PS matrix is the number of thrust source rows by the number of power source columns. So since we have one propeller, we're going to have one row. And since we have two power sources, the electric motor and the turboshaft engine will have two columns. Similarly, the power source matrix is going to be 2 by 2 because there's two power sources. And then the power source energy source matrix is going to be 2 by 2 because we have two power sources and two energy sources, the battery and the fuel. So going back to the connections, we can see that the electric motor is connected to the fan or propeller, as well as the turboshaft, which is why we have this 1-1 here. Now, you'll notice that in the parallel hybrid configuration, none of the power sources are connected in series like they are in the turboelectric and the series hybrid case. So what we say is that the power sources are not driving anything else but themselves, which is why we have the 1s on the diagonal of the PS-PS matrix. The electric motor is driving itself, and the gas turbine engine is driving itself as well. Lastly, we'll look at the physical connections between the power sources and energy sources. So the electric motor is only connected to the battery, hence the 1 here in the 1-1 entry. But since the electric motor is not connected to the fuel, we put a 0 in the 1-2 entry. Similarly, the turboshaft engine is not connected to the battery, hence the 0 in the 2-1 entry. But the turboshaft engine is connected to the fuel, giving us a 1 in the 2-2 entry. We can do this for the turboelectric aircraft, this turboelectric propulsion architecture as well. So if we look, we have one energy source, 3 power sources, and 1 thrust source. So we know that the TS-PS matrix is number of thrust sources by number of power sources. So it's going to be 1 by 3. The PS-PS matrix is number of power sources by number of power sources, hence a 3 by 3 matrix. And then there is one energy source. So we're going to have 3 rows by 1 column in the PS-PS matrix. And again, we only have the electric motor driving the fan or propeller. So we have 0, 0, 1 because the turboshaft and generator are not connected to the fan, but the electric motor is. For the PS-PS matrix, all power sources drive themselves, which is why we have the 1s on the diagonal. But then the turboshaft is driving the generator. So the first power source is driving the second one, hence the entry in the 2-1. And then the generator is driving the electric motor, hence the entry in the 3-2 part of the PS-PS matrix. And one way I like to think about the connectivity is that the columns of the matrix are driving the rows. So for example here, column 1 drives row 2, so the turboshaft drives the generator. Similarly, column 2 is driving row 3, so the generator is driving the motor. Now, for the PS-ES, there's only one connection between the turboshaft engine and the fuel, which is why we have 1, 0, 0. you can see a similar set of TSPS and PSPS matrices for the series hybrid, except you'll notice that we have to account for this battery connection to the electric motor. So previously, we just had the 100 column for the turboelectric case, but now this electric motor is also connected to a battery. So we have to add another column to the PSES matrix because we have two energy sources now. And since only the electric motor connects to the battery, we leave the first two entries in the column as 0 because the turboshaft engine and generator do not connect to the battery, but the electric motor does, hence the 1 in the 2-3 entry. So this is a quick summary of how these connectivity matrices are built, and you can read more about it in the paper. I have the citation listed below for you to access. Now, this is only one of the interdependency matrices we need to develop in FAST. We also have to develop interdependency matrices to show how much power is being split between branches of the propulsion architecture. So if you see here in the parallel hybrid, the branch with the electric motor is going to contribute some fraction of the total power required, and the turboshaft engine will have to contribute the rest. So what we'll do in the next video is we'll make propulsion architecture matrices for a new propulsion architecture, and then we'll also introduce these operational interdependency matrices such that we can prescribe how much power is coming from each branch. And then on top of that, we'll introduce efficiency matrices. And the efficiency matrices allow us to account for the fact that all of the components are not transferring 100% of its input energy. All the components have some sort of losses along the way. And that's what we'll be taking a look at in the next video. So we'd like to thank you for watching this one. I hope the explanation of the propulsion architectures and the matrices made sense. If you need more details, make sure to check out the paper that I had in the citation on the previous slides. And we will see you in the next video where we're going to make our own propulsion architecture, as well as the interdependency matrices that go along with it. So again, thank you for watching. Make sure to check out the Ideas Lab at ideas.engine.umich.edu.